Hello, and welcome to this video. This is the second video in the three-part lecture video on parametric surfaces and surfaces of revolution. In the first part, we discussed vector-valued functions in two parameters u and v, whose graphs are referred to as parametric surfaces. If you have not yet watched the first video, please watch it first before proceeding with this video. For this part, we discuss how to obtain vector equations for so-called surfaces of revolution. Let's begin. Suppose we have a plane curve defined by y equals f of x with f of x non-negative, as shown in the figure. Consider the surface generated by rotating this curve about the x-axis. We see the resulting surface S, called a surface of revolution or SOR for short, in the figure. In Math 22, Cartesian equations for SORs were derived. Here, our goal is to obtain a parametrization of the SOR. To this end, we focus on a particular point xyz on the SOR. Denote by theta the angle formed when the point on the curve y equals f of x was revolved about the x-axis to obtain the point xyz. Since the curve has equation y equals f of x, then the length of this segment must be f of x. In addition, since the axis of rotation is the x-axis, this segment here is also of length f of x. Thus, we obtain a parametrization of the SOR by setting x equals x, y equals f of x cosine of theta, because the y-coordinate of this point is precisely the length of the side adjacent to theta in this right triangle with hypotenuse f of x, and z equals f of x sine of theta, because the z-coordinate of this point is the length of the side opposite theta in the right triangle. Note that the parameters here are x and theta. Similar arguments show that an SOR obtained by revolving the plane curve y equals f of z with f of z non-negative about the z-axis has parametric equations x equals f of z cosine theta, y equals f of z sine of theta, and z equals c. The same holds for an SOR obtained by revolving the plane curve x equals f of y with f of y non-negative about the y-axis. Such an SOR has parametric equations x equals f of y cosine of theta, y equals y, and z equals f of y sine of theta. Observe that in all parametrizations, the parameters are theta and the variable corresponding to the axis about which the SOR was revolved. Before we continue to the examples, let us go back to the SOR obtained by rotating the curve y equals f of x about the x-axis. Notice that the same SOR is generated if we revolve instead the plane curve z equals f of x about the x-axis. This time, we let theta be the angle formed when the point on the curve z equals f of x was revolved about the x-axis to obtain the point xyz on the SOR. With this definition of theta, we get another parametrization of the SOR given by x equals x, y equals f of x sine of theta, because this time, the y-coordinate of the point xyz is the length of the side opposite angle theta in this right triangle with hypotenuse of length f of x. And z equals f of x cosine of theta, because the z-coordinate of the point xyz is the length of the side adjacent to theta in the right triangle. As you can see, the difference of this parametrization from the previous parametric equation is that the expressions for y and z are interchanged. We now illustrate what we have discussed in the next two examples. In the first example, we are being asked to find parametric equations for the SOR generated by revolving the plane curve y equals e to the minus x about the x-axis. The figure on the left shows the SOR. The curve y equals e to the minus x is located in the xy plane, and the SOR is obtained by rotating the curve about the x-axis. From our discussion, we conclude that a parametrization of the SOR will have parameters theta and x, since the axis of rotation of the SOR is the x-axis. Hence, parametric equations for the SOR are x is equal to x, y equals e to the minus x cosine of theta, because our plane curve is y equals e to the minus x, and so f of x here is e to the minus x. And z equals e to the minus x sine of theta. Furthermore, we get another set of parametric equations for the SOR by setting y equals e to the minus x sine of theta and z equals e to the minus x cosine of theta. Remember that such parametrization is obtained if we consider the generating curve for the SOR to be the plane curve z equals e to the minus x in the xz plane. For the second example, we need to give parametric equations for the hyperboloid of one sheet 4x squared minus y squared plus 4z squared equals 4. The figure on the right shows the hyperboloid of one sheet. Observe that the traces of the hyperboloid in planes parallel to the xz plane are circles. This implies that the hyperboloid may be obtained by rotating this red curve about the y-axis. Notice that the curve is half of the hyperbola, which is the xy trace of the hyperboloid. The xy trace of the hyperboloid is the hyperbola 4x squared minus y squared equals 4. And so, this curve, which lies on the portion of the xy plane where x is positive, has equation x equals 1/2 of the square root of 4 plus y squared. Recall that a parametrization of the hyperboloid, now viewed as an SOR, will have parameters theta and y, since the axis of rotation of the SOR is the y-axis. Therefore, parametric equations for the hyperboloid are x equals 1/2 square root of 4 plus y squared cosine of theta, because our plane curve is x equals 1/2 square root of 4 plus y squared, And so f of y here is 1/2 square root of 4 plus y squared. Y equals y, and z equals 1/2 the square root of 4 plus y squared sine of theta. We have now reached the end of the second part of the lecture video. Please continue and watch the third and final part of the lecture video. In the next part, we will look at tangent planes to parametric surfaces. Thank you for your attention and good day.